All right, you guys. Welcome to Wednesday, October 7th, halfway through the week. Hopefully, the virtual learning is going okay. It seems to be going pretty well so far. You guys are communicating. It seems like when you have questions, hopefully, the videos are going well. Hopefully, you guys have your own earphones, and so you can kind of work totally independently during class. I know it's not the ideal, but at least we're continuing to be able to provide instruction and learning. So we'll just make the best of it. We'll finish out this week, hopefully, without too much as far as a hiccup. And then hopefully next week I'll be back and we can kind of get back into something a little bit more fluid and normal. Okay? So what I guess I just want to bring back up is the fact that, yesterday we took kind of an extensive amount of notes. We did a kind of a discussion on how you write set builder notation and what it looks like. Set builder notation is just a way of describing a set of numbers as opposed to listing it, or as opposed to writing it out in sentence form, using these elements or these symbols like element of, using inequalities to express them, using expressions to express them. So set builder notation is really just kind of a, this hybrid way of writing things in a very condensed fashion, but being very descriptive and very formal with our writing, okay? And then we transferred from, set builder notation into interval notation. Interval notation, super simple, it's just basically a shorthand version of saying, it's all the numbers from here up to here. So like, when you have the interval from -2 to +1, if this is a solution set, this is the way you write it in interval notation. It's the solutions from -2 up to 1. And then obviously you get infinite sets, like x is greater than or equal to 1. You'd say that's the set from 1 up to infinity. The bracket indicates, you're including, so it's the equivalent of basically a closed dot or a solid line. There's a lot of like parallels between, inequalities, intervals, stuff like that. And then the only one that's kind of a little bit weird is when you have infinite sets that are less than, they go to negative infinity. So, if your solutions are all numbers less than or equal to -4, I mean, typically the way we would say that is we'd say it's all numbers from -4 to negative infinity, but that's the numbers smaller than -4. So if we want to write it in interval notation, we have to say it's the numbers up to -4. So from negative infinity up to -4. So this is basically where we should have, or where we kind of left off yesterday. If you have questions on the assignment, you can still shoot those to me. I didn't receive a whole heck of a lot of questions yesterday, but I'm anticipating it's just because we didn't have a lot of questions, okay? So if at some point I feel like there are some questions, I might double back in one of these videos and or elaborate on those, but for now we're just going to continue moving on, okay? So the part that I really want to focus on is actually back up here before I turn the page here. And I'm just going to have you guys pick right back up where we left off yesterday. So I did have you guys copy all this stuff into your notes. These capital letters that are the names of the sets of numbers, kind of a re-exploration of what a function actually is, and then some examples of both types of notation. But like I said, before we continue on here, and before I flip the page to my next stuff that we're going to just add on to section 1.1's notes, I do want to just kind of go back and double back to the word function. And remember, a function is just a set of ordered pairs. So it can be written as a set of ordered pairs like this. It can be a bunch of ordered pairs together as a graph, and it can be that graph's equation. So we sort of at one point brought this up, but then we left it. If you have the equation y equals 2x squared minus 3x plus 4, everybody knows that quadratic equations make parabolas. Parabolas pass the vertical line test. So technically a parabolic equation, which is a quadratic equation, is also considered a function. It passes the vertical line test, which is the function test. So what we say is we can rewrite this in function notation. Instead of y is equal to all this stuff, we say it's a function of x, or f of x is equal to 2x squared minus 3x plus 4. What we're going to do today is we're going to focus more of our attention on functions, okay, the equations that are functions and what we can do with them and what function notation allows us to sort of shorthand do with them, okay? So this is really kind of our starting point for today, and I'm not going to lie to you guys, I'm kind of winging this and seeing just how far we can get, or how far I feel comfortable getting with this stuff before I make an exact decision on what I'm going to have you guys working on for tomorrow as far as an assignment. So I gotta keep myself super organized because I got all my stuff in here for algebra, advanced math, and calc, okay? So, like I said, I was at the bottom of my sheet of paper, so I'm on to the next sheet of paper here. This is still section 1-1. You're not going to start a new heading, so I think it's a good idea that everybody take notes. If you choose not to, that's fine. That's up to you entirely. But if you are taking notes, just go ahead and copy this direction or these directions for the examples down, all right? And like I said, I'll try and kind of pace myself just a little bit here in the understanding that probably there's a handful of people or maybe the majority of people who are going to take notes as we go through this, okay? So here's what you're going to be working on for sure as part of your assignment today, okay? I'm going to give you something or an equation written in function notation. In this case, it doesn't say f of x. The f technically stands for function, but it's really an arbitrary variable. So it can say f of x equals x squared plus 8x minus 24. It can say g of x. Kind of the function notation is just there as a way for us to distinguish which function we're talking about in a specific situation. So what you can see here is the function g of x is another quadratic equation, just like the example that I was just kind of pointing back to on that last one. So there's a lot of stuff that we know about this. We know that if we were to graph this, it would be a parabola, which is a function, which is why it can be written in function notation. But what we're going to do today is we're going to take advantage of this function notation, and we're going to evaluate the function for each specific input, okay? So part A says evaluate this. Technically, the way we read this is we read this as g of 6. Okay, so I'm going to do kind of some extra stuff maybe off to the side. I'll tell you what I do or do not want you necessarily to draw as we go through this. But put simply, this is a very simple thing, all right? So for part A here, what this basically means is take this function y equals x squared plus 8x minus 24 and literally plug in 6 in the place of x. So essentially what we're doing here, you guys, is we're going to plug in 6 for both of those x's, and we're going to see what it kicks back for y, okay? So the way that we're going to write this is we're going to say g of 6 is 6 squared plus 8 times 6 minus 24. Okay, so it's very simple. All we're doing is plugging in 6 and we're seeing what it gives us as a result for the function's value. So this would be 36 plus 48 minus 24. 36 plus 48 minus 24 is going to be 60. So here's how you're going to write your answers to these questions today. You're going to say g of 6 is 60. Here's what that means, you guys. It means, real simply, when you plug in 6 for x, you get y equals 60. So when x's value is 6, the corresponding y value is 60. So if you were to try and graph that, which obviously we don't want to, the point 660 would be a point on that guy's corresponding parabola. But we're not focused so much on that. We're focused on sort of like, like what shorthand does function notation allow us to do? Function notation allows us to know which equation to plug into and what to plug into it. So if we had a separate function here and I called it h of x, right? Like if I just put one up here, you don't have to write this, but if I put it up here, h of x equals 4x cubed minus 3. Okay. Function notation just allows us to have two separate equations, y equals x squared plus 8x minus 24 and y equals 4x cubed minus 3. But by labeling them different function names, g of x and h of x, for part A, part B, and part C, I know which equation I'm plugging into. For all three of these, I'm plugging into the g function, which tells me that if those are the only three parts, this h function really doesn't have any bearing on this problem. Okay, that's sort of the whole point of function notation, is it's just a shorthand way of being able to know which function we're plugging into. So when part B says g of negative 4x, that means go to the g function, which is the first one here, and just everywhere you see x, replace it with negative 4x. So we're going to do that here. When we plug in negative 4x, for x squared. So it becomes negative 4x squared plus 8 times negative 4x minus 24. Obviously, when we're plugging in an expression, we're not going to get a simple number. We're not going to get just a simple function value, okay? So all we do to this is we plug it in and then we simplify. We clean it up to the best of our abilities. Negative 4x squared is negative 4x times negative 4x. So negative 4 times negative 4 is positive 16. And then we're obviously going to have an x squared there. Right here, 8 times negative 4x is negative 32x. The minus 24 comes down. We don't have anything to combine it with. So literally, this is what we write. We say that g of negative 4x is the polynomial 16x squared minus 32x minus 24. Okay? So you'll notice that your homework today is very direct. It's very simple. You know, it's just function evaluation. So you're taking a function notation equation and you're just being told what to plug in, and once you plug it in, you simplify. And every once in a while on most of these, there's going to be part of it where you're going to be plugging in an entire expression or a binomial like this. Part C says evaluate g of 5c plus 4. Well, g of 5c plus 4 means go to the g function and everywhere you see x, plug in 5c plus 4. So here's what it becomes. X squared from my original function becomes 5c plus 4 squared. The plus 8x becomes plus 8 times 5c plus 4. And then obviously if my function ended with a minus 24, I need to end mine with a minus 24. So you'll notice that all you really have to do to this is clean it up. So the obvious part here is this. We're going to take the positive 8 and we're going to distribute it to the 5c plus 4. The part I need everybody to just embrace here, and I'm really only going to show it to you this one time because it's pretty straightforward, and once I show you, everybody will recognize it. This 5c plus 4 squared, you don't just distribute the 2, okay? It's not just 5c squared, which would be 25c squared, plus 16 for 4 squared. You don't just square both of those. Instead, when you have a binomial, 5c plus 4 squared, you have to rewrite it like this, 5c plus 4 times itself. And I think everybody will recognize the reason that we break it apart like that, 5c plus 4 times itself, is so that everybody recognizes to multiply these together, to actually square a binomial, you have to FOIL. Okay, so it's not just 5c squared and 4 squared, it's going to be a bunch of other terms. So it's 5c times 5c, which is 25c squared. There's a 20c, so plus 20c. And then when I distribute my 4, I'm going to get another 20c and then a 16. So you'll see it's not just the 25c squared and the 16. You also have a middle term that's going to come out of this. Now, what I want everybody to read or see right now is those 4 terms are just 5c plus 4 squared. I still have to bring down these 2 terms once I distribute 8 and the minus 24 at the end. So here it is, 8 times 5c is plus 40c, 8 times 4 is plus 32, and then bring down the minus 24 at the end, and all it is from here is just combining like terms, okay? So this is my only c squared in the problem, so it can come down, 25c squared. There's a whole bunch of c's and a whole bunch of constants. So 20c plus 20c plus 40c is 80c. So when I put all my c's together, I get 80. And then I gotta add 16 plus 32 is 48, minus 24 is positive 24. So when I plug in the expression 5c plus 4 into the g function, what I'm left with is another quadratic polynomial. This time though, it's 25c squared plus 80c plus 24. Okay? So what you'll notice today on today's portion of the assignment is this is all it's going to be. They're going to give you equations written in function notation, and then they're going to ask you to evaluate different values. But basically all that is it's going to tell you what to plug in, either plugging in a number and getting a number, like in part A, or plugging in an expression, you know, hopefully it's just a single term like part B, because then it's not as much work. But if it is plugging in a binomial expression, then you will end up having to FOIL if it's squaring or cubing or something like that. Okay? Now, this next piece, and I just kind of peeked at my clock here, I don't think we're going to get to the point where I'm going to give you guys this on your homework today. But I do want you guys to add this to your notes so that we can kind of start with it already in our notes tomorrow, okay? What we're going to look at now is we're going to look at what are called piecewise defined functions. And we're going to explain this, like sometimes it scares people when you hear the expression piecewise defined, and then it really freaks people out when they see this right here. F of x equals this great big brace, and it's three separate things. It's 4, comma, x is less than or equal to 3, negative x plus 1, comma, negative 3 less than x, less than or equal to 0, and x squared plus 1, comma, x is greater than 0. This tends to freak people out, but all I need you guys to do is add this to your notes today. A piecewise defined function is just simply a function defined differently across its domain. Okay? A function defined differently across its domain. What that means is that for different x values, because that's what domain values are, they're x values, for different x values, the function itself is defined as completely different equations, okay? So I'm going to show you exactly what this is and exactly what it looks like, and then tomorrow you'll see the work that goes along with it, okay? So for now, all I want you guys to do is just basically copy this whole thing down. F of x equals a big brace 4, and then x is less than or equal to negative 3, negative x plus 1, negative 3 is less than x, less than or equal to 0, and then x squared plus 1, x is greater than 0. All I need you guys to do is just simply copy that down right now, and then we're going to kind of build on this. I'm going to have you add a couple things to your notes, and then we're going to call it good enough once we get this kind of like generally understood, okay? All I need basically everyone to understand right now is this. This is just a condensed way of writing 3 separate equations. Okay, this where it says f of x is equal to, and it's all of this stuff combined. What I need you guys to understand is this is just 3 separate equations. It's the equation y equals 4. That's this, y equals 4. Then the next one is y equals negative x squared plus, or excuse me, negative x plus 1. And then it's the equation y equals x squared plus 1. So, at the surface level, a piecewise defined function is just, in this case, 3 separate equations that are squished together into one. So instead of rewriting y equals or f of x equals 3 times, they write it once, and then they just have the 3 other parts put together up here, okay? So if you guys think about this next part, don't write. Don't draw this next part. If I were to graph all 3 of those equations. You don't have to, you're going to draw a graph up here, and you're going to actually draw what this piecewise graph looks like. But basically, here's the deal. Y equals 4 is just a horizontal line through 4, right? You go to the y-axis, you put it down at 4, you draw a horizontal line. This is a linear equation. It's got a y-intercept of 1, and then you've got a slope of negative 1. So down 1, right 1. This is just a diagonal line that looks like that. And then this is a parabola, y equals x squared plus 1. It's a generic parabola that's vertex is up 1 unit, and then it's got basically just like a slope of 1. So it's just a regular parabola that looks like this. Okay? So here's the whole graph of y equals 4. Here's the whole graph of y equals negative 1x plus 1. And here's the whole graph of y equals x squared plus 1. A piecewise graph, or a piecewise defined graph, basically does this. It tells you to take these 3 graphs and splice them together. So this is the part you guys can draw, okay? So in your notes, you can just draw an x-axis like this, draw a y-axis, you need to be up a little bit more than you need to be down. So you need to be above the x-axis a little bit better than you need to be below it. Okay, so here's what I'm gonna do. I'm gonna go 1, 2, 3, 4, 5. Okay? All we're gonna do on this graph right here, you guys, is we're gonna draw all 3 of these graphs, but not the whole thing. Okay? That's what this is. This is the domain restriction. This is where it tells us where to draw each one of these. So for this top one, for y=4, this horizontal line, what it tells us is just draw it for x values less than or equal to -3. So x values less than or equal to -3, that basically tells us we're gonna draw it over here. Okay, so instead of like going to the y-axis and putting a dot at 4, I'm going to put a dot up 4 units, but at -3. So -1, -2, -3. I'm going to go up to 4, and I'm going to put a dot there. But instead of drawing this whole horizontal line, I'm only going to draw it to the left of -3. Okay, that's what this means. If we interpret this side to side, because that's what domain values are, they're the horizontal values of a graph. X is less than or equal to -3 means to the left of and at -3. So to the left of and at -3, I draw that portion of that horizontal line. Okay? In between -3 and 0, because that's what this says, for x values between -3 and 0, so that would be in this range right here, from -3 to 0. In this window right here, that's where I draw my horizontal line. So you got to be kind of creative with this, but I'm going to put a dot. So, okay, for x equals 0, it says for x is less than or equal to 0, I'm going to put my y-intercept right here. So I'm going to put a dot at 1 for my y-intercept. But instead of going down and to the right, because that's what I did right here, remember I went down and to the right, I have to remember I'm only graphing this to the left. I'm graphing it between 0 and -3 in this graph. So instead what I'm going to do, instead of going down and to the left, I'm going to go, or excuse me, down and to the right, I'm going to go up and to the left, up and to the left. And what we realize is if I go up one, back one, over and over, I actually get right back to this dot right here. So there's that. These two graphs actually meet together at that -3, 4 point. Because again, my y-intercept is 0, and if I go up one, back one, up one, back one, up one, back one again, I actually get right to that point. So it's like this line and this line merged. And then for everything to the right of 0, for my domain or my x values to the right of 0, this says draw the third and final graph, the parabola. Well, you'll notice my parabola was up 1 unit as well. And by the way, I set this one up on purpose. The first example we're going to look at tomorrow of a piecewise function, they're not going to mesh quite so nicely like this one did, where this horizontal line met that diagonal line, and that diagonal line is going to meet the parabola. But I wanted to draw one that worked out really, really clean for this first example. Okay, this graph now is a horizontal line mixed with a diagonal line mixed with a parabola. The horizontal line is to the left of -3 because that's where the domain told us to draw the horizontal line, less than or equal to -3. The diagonal line only spanned from -3 to 0 along my width of my graph, my x-axis, and then everything to the right of 0 is the parabola. So again, it's the blending or combination of these 3 graphs, but over a broken domain. Okay, this whole point of this piecewise function is it splits the entire domain into 3 separate things. Everything to the left of -3 on my picture, everything between -3 and 0 on my picture, and then everything to the right of 0 on my picture. So what you need to really understand is we're breaking down the horizontal picture from side to side into 3 separate chunks and just drawing portions of these graphs. That's what a piecewise defined function is. Okay? So by you guys having this, all right, and I understand I told you guys you didn't have to draw these three little graphs down here. You just needed the actual graph of the piecewise function. But by having this kind of general understanding, that's going to allow us to go a lot quicker tomorrow and really get into how we're going to kind of blend the idea of, evaluating functions when some of the functions are going to be piecewise functions. And then we will talk a little bit more about the whole graphing nature of piecewise defined functions as well. Okay, but for now, when you guys, when you close out of the video, you get started on your assignment. Your assignment today should be relatively simple because for the most part, all it's going to be is this stuff up here. Okay, it's going to be evaluating functions for specific expressions, either numbers, expressions, binomials, whatever the case may be, but it really should not be that terribly difficult. Okay? So I'm going to cut it off there. We're going to do the same thing tomorrow that we did today. We're going to pick right back up here because this example is not even done. All right, we're going to finish this example. I'm going to show you the extra piece of this. Then I'm going to show you another example, excuse me, of a piecewise function, and we're just going to keep picking back up with this a little bit at a time until we get through this first section. All right, a lot of information in this first section for us. All right, guys, that'll wrap things up for today. Have a good rest of the day. Keep those questions coming if you do have them, and just let me know, all right? Things are going all right now. Let's just keep our forward momentum going and make it as good as it can be. All right, guys, have a great day. I'll talk to you later.